In this video, we'll talk about some odds and ends of Fourier analysis. One detail of Fourier transforms that the math implies, but we don't talk about a whole lot, is that the Fourier transform expects all of the data that goes into it to be periodic. Now that's a little bit tough because the finite size of your oscilloscope's memory forms this window of time that you can look at your signal for. And unless you're really lucky, that window isn't going to fall exactly on one period of the signal. So that's a problem because your FFT assumes your signal goes on and on exactly with a period of one window forever. So the FFT, the piece of math you're using, thinks your signal looks like this, which is particularly bad because it means your FFT is assuming that you have a periodic discontinuity right here. And that means it's going to add a whole bunch of high-frequency sinusoids that aren't really there in order to explain the periodic continuity. This is a problem, but it's a really well-studied and fairly easy to fix one. If you multiply your function by a window function that goes to 0 at the sides of the window, then there can't get a discontinuity when it gets repeated. So problem solved. One vocabulary note, these window functions have different names. The simplest one is called a rectangular window, which is the same as not applying a window function at all. Some other common ones that you can find include Hamming windows, Hanning windows, and Blackman-Harris windows, and your scope can apply these automatically. Another question that might come up is, what if my sample is too short to fit into a window? If you just fill in the rest of your sample with zeros, it works out fine. That's called zero padding. Another thing you need to be mindful of when you're measuring waves is your sample rate. Underwater acoustics often operate at ultrasound frequencies, which are north of 20 kilohertz, though in your case you'll be measuring much more annoying audible range sound waves. So in order to get us thinking about the sample rate, I'd like you to pause the video and try to answer all of these questions. Alright, so to measure a 10 kilohertz pressure wave, we need to make sure we're sampling at least 20 kilohertz because the Nyquist rate is twice the highest frequency in your signal. Fortunately, the sample rate of the scope is very fast. It caps out around 100 megasamples per second. So that's the answer to this question. However, if you're trying to measure signals for a really long period of time, the oscilloscope will throttle its sample rate to stay inside of its sample memory. So be careful you don't measure too long and accidentally alias your signals. And that throttling of your sample rate is what happens when you hit your scope's memory limit. Finally, although your teensy was capable of sampling at like 100 kilohertz in Lab 2, your robot is programmed to sample at only 10 hertz. So you need to write some fancy software or do some tricky circuit design to measure audio in your final project. And that's why we were trying to get you to meditate on this question. Your professors are very ready to help you out with that software or hardware. So in summary, be sure to apply a window function to your data and keep an eye on your sample rate, which is going to vary depending on the length of time you're sampling with your scope or on how you're using your teensy.